Hi, my name is Byung-Soo Kim, and I'll present our work on automated test generation for REST APIs. No time to rest yet. This is joint work with Trisin, Sarb Sinha, and Alessandro Orso. REST APIs are widespread. The last decade has seen a growing number of web services deployed. Many of today's well-known web services, such as YouTube, Spotify, and GitLab, provide RESTful APIs to access their resources. Martin Lopez reported in 2017 that, according to Programmable Web, which is a famous API repository, more than 80% of the APIs are recorded in their directory. Another popular repository, apis.group, contains thousands of APIs. Before we move on, what is REST? REST stands for Representational State Transfer. RESTful guidelines enable lightweight and flexible implementation of the APIs, which makes REST APIs increasingly popular. The client can access the resource via the REST API provided by a web service by sending requests. The request typically contains resource path, HTTP method, headers, and body. The response is made of headers, body, and status code. Status code indicates whether a request has been successfully completed. 200 status code means the request has been successfully processed. User gets 400 status code when there is a client-side error so that the request cannot be processed. 500 status code means there is an internal server error. There are typically descriptive languages such as OpenAPI specification, RAML, and API blueprint. They specify in what format the input and output of the API should be. The client and web service are expected to make requests and responses conforming to the specifications. Here is an example of the OpenAPI specification of a service called Feature Service. As you can see, it specifies the resource path, the HTTP method, the available input parameters, the response status code, the response body format, and so on. You probably have seen many of these kinds of server failures. Web services with REST APIs are widespread, and these services have large numbers of client apps and third-party integrations. Therefore, service failures can have huge and widespread consequences. This is why these services' correctness, security, and reliability are critical and need to be tested. For this reason, many automated testing techniques have emerged in recent years. These techniques leverage the descriptive languages, mostly OpenAPI specification, to produce test cases exercising various functionalities of the web service and detecting bugs. However, because these techniques use different strategies and oracles for testing, it is hard to compare each other. Also, they were evaluated on different benchmarks with different metrics, so it is hard to access their strengths and weaknesses and understand how they actually perform. For this reason, and to fill this gap, we conducted an extensive empirical study by comparing state-of-the-art REST API testing tools in terms of code coverage and bugs found on a benchmark of 20 RESTful web services. We analyzed their performance, discuss implications, and present possible improvements. We searched for REST API related papers published since 2011 in top venues in software engineering, security, and web technologies. We identified relevant papers via keyword search using the terms REST, API, and test, and checked citations in the identified papers. Among the resulting set of papers, we selected techniques and tools that first rely on well-known REST API standards such as OpenAPI, RAML, and API Blueprint, and second, produce actual test cases. Finally, we collected 10 tools: EvoMaster WB, EvoMaster BB, Wrestler, RustTestGen, RustTest, Schemathesis, Dread, Tcases, VBoxRT, and API Fuzzer. EvoMaster has two ways to run it: white box mode and black box mode. EvoMaster WB stands for EvoMaster white box mode, and EvoMaster BB stands for EvoMaster black box mode. To create our evaluation benchmark, we first selected RESTful web services from existing benchmarks used in the evaluation of VBoxRT, EvoMaster, and RustTest. Among those, we focused on web services implemented in Java Kotlin and available as open source projects so that we can use EvoMaster WB. This resulted in an initial set of 30 web services. We then searched for Java Kotlin repositories on GitHub using tags REST API, RESTful API, REST service, and RESTful service. Then, we ranked them by the number of stars received, selected the top 120 entries, and eliminated those that did not contain a RESTful specification. This additional search resulted in 49 another web services. We tried installing and testing this total set of 79 web services locally and eliminated, first, services that did not have OpenAPI specifications; second, services that did not compile or crashed consistently; third, services that the majority of operations relied on external services with request limits. So now, we have 20 RESTful services shown in the picture. From the collected services and testing tools, we had 3 research questions. First, how much code coverage can the tools achieve? Second, how many error responses can the tool trigger? Third, what are the implications of our findings? To answer those questions, we used line branch method achieved code coverage. Also, number of failures is measured as 500 status code with error stack trace to exclude the overlapped errors. To run the experiment, we used Google Cloud E2 standard for machines running Ubuntu. Each machine had 4 Intel Xeon processors and 16GB RAM. We ran 20 services and 10 tools for 10 times with an hour option. We ran each tool with the recommended configuration settings as described in the tools paper or user manual. Also, we reset the environment after each run. The table shows the achieved line branch method code coverage in an hour and error, unique failure point, unique library failure point. The result shows that EvoMaster WB performed the best on all the metrics. Tcases found the most number of bugs among the black box tools. EvoMaster BB and Wrestler ranked second and third among the black box tools. Now, let's see how the analysis of these results lets us answer our research questions. Our first question was how much code coverage the tools can achieve. From the last slide, we observed that the tools achieved low code coverage. We found 3 significant causes. First, operation dependency was not detected. Second, there were mismatches between specification and API. And third, the appropriate parameter values were not generated. Firstly, operations often have a producer-consumer relationship. As an example, a user ID should be generated before searching for that user ID. So, it's crucial to generate the stateful test cases taking into account existing operation dependencies. Secondly, the specifications we observed were not always correct. There were mismatches which negatively affected the tool's performance. Lastly, parameter generation was limited. For example, if a parameter description stated put your email in a given field, the tools generated a random string anyway because they did not process the natural language descriptions. The second research question was about the number of error responses the tools could trigger. The white box tool EvoMaster WB was the best performer by a wide margin. However, in some cases, black box tools performed better than white box tool EvoMaster WB using the specification information. Specifically, black box tools that used example keywords sometimes explored more code with the benefit of example value and found more bugs. We also found that exercising operations with various parameter combinations and various input types helped reveal more faults. As we saw strong correlation between achieved code coverage and found bugs, we can conclude that somehow, unsurprisingly, achieving higher coverage usually also triggers more failures. Lastly, the severity of different 500 errors can vary considerably. Failure points in the service code usually occurred at throw statements following checks on parameter values. Failure points outside the service code, however, often involved erroneous requests that had been accepted and processed, which could lead to severe failures. We now discuss some of the main implications of our results and some possible future research directions. First, based on our findings, one promising research direction is having better input parameter generation strategies. In particular, we believe that symbolic analysis of the code and more sophisticated testing techniques such as combinatorial testing at two-way or higher interaction levels would be promising directions to pursue. Using sample values for input parameter generation can indeed lead to better tests. We implemented a proof of concept text processing tool that extracts possible parameter values from the parameter descriptions and applied the tool to two services, OCVN and Language Tool, for which the existing testing tools failed to obtain high coverage. With the help of our tool, we identified developer-suggested values for 934 of the 2,923 input parameters. We believe that better support for stateful testing is also necessary to improve the effectiveness of REST API testing. We found that even simple word similarity matching for request and response parameters could help to improve the performance of the REST API testing. You can refer to the paper for a complete and detailed list of implications and corresponding possible research directions. We conclude by discussing some of the future work we are planning to perform. First, we'll extend our work by considering more REST services and testing tools. Second, we'll investigate the use of NLP-based techniques because we observed that the natural language part of the API specifications can contain helpful information. We also want to seed faults using mutation and use their kill rate as an additional measure of effectiveness of the input parameter generation techniques. Lastly, we want to add symbolic analysis capabilities to improve input generation. Thank you for your attention, and I am open to questions.